too, okay, and you have weights assigned to it. The weights are given because you might want to tell, okay, when people are given an option to choose a number, the likelihood of choosing 7 or 4 or 5 is some x, okay. So that x is what you provide to as part of the weights, right? I'm just giving you an example. Or like if people are given an option to choose color, the likelihood of choosing the blue is like, is what the or green is what the you give to the weights, the values as weights. But when you say like, most people choose blue, then that is a bias, okay. So we will see like, how bias also acts, because we need that bias also as part of the equation here, you see, which is needed to tell the output accurate, right? When a child is posed with some a picture, an object of an or like if a child sees an animal, right, it can tell like from the experience it's a cat or a dog, because sometimes the child tells identifies the animal as a wrong one, right? It would say as a goat or something like that, because it would have never seen that before. So but it will, the child will try to make use of the past experience, and it will, the child will perceive the features of the input, like the face of the dog or the face of the, right? And if the prediction is wrong, if the identification or the outcome itself is wrong, let's say the child says the goat as a dog, because the child has never seen a goat in the lifetime so far. So the parent or the guardian will tell, no, it's not a dog, it's a goat. So that is like, you are giving a new classification or a new label, or like you are identifying a new object altogether, and the child basically remembers it the next time, okay, because like a new input has been given, a new label has been given. So what happens is, if the next time, like if the child is encounters the sort of data, obviously may it be like, any the data science or machine learning model that you applied previously, or the deep learning model, when the data set is huge enough, the accuracy of the result is going to be higher, like the efficiency and the accuracy is going to be on the top. But traditionally we didn't have much of the computing resource, we didn't have the approach of parallel processing and horizontal scalability to handle a lot of data. Today we have all those comfort, we have all those luxury. So that is why we will apply the data learning, the deep learning, right? And next point is, the algorithms have been like, Google image search back in 2012 or 2011. The image search was not so accurate. It was giving a somewhat inaccurate result, and it wasn't giving, right. That like how is possible is because of the huge data set that's being uploaded onto the ImageNet, and lots of optimization being done on the algorithms and libraries, okay. So a lot of cool stuffs are happening on the programming space, right? So that's why I hope these three are more than enough to have as part of our motivation to use deep learning for time series forecasting and time series data handling. So any questions so far? Okay, I'll take it as no. Coming on to the frameworks, we saw about the deep learning, the basics, the neural networks. So we need to implement this concept of neural networks with some programming libraries, right? Like the practically we have to apply it with some libraries or APIs. So these are like the top libraries which help, you know, which the machine language. The assembler language is the closest one to the hardware, and after that, C is the fastest one. Because we need to take a lot of inputs. As I told before, like when we have a layered computation, we need to have lots and lots of events happening at the same time, and lot of inputs being given to the system, and the processor, like the graphical processing unit, has to give you some result for every single event or action being performed in the environment. So for that, C was chosen. But machine learning programmers, data scientists, data science professionals, they are pretty much adapted with Python or R. Okay, so these libraries have some APIs to being interacted with Python also, or MATLAB, or even some there are certain lesser common frameworks which are available for R with deep learning. Okay, so that has been addressed as well. Okay, now let's come on to with the deep learning types. Okay, so I'd rather say this is neural network types. Okay, why? Because they are one and the same. Like if you ask me, like being in industry, I would definitely try to abstract things. A, for the, like, I'm opinionated about it. B, we discuss a lot about these stuffs, and we don't want to repeat every time again and again. We know, we know what it is. We can generalize stuffs. It's okay to do that. So in that way, I would say neural nets and deep learning, or AI even, I would say, neural nets and AI are one of the same, I would say. I mean, of course, like if you go by the textbook definitions, they're not same, but still, we can generalize things over there. So the most common neural networks, I mean, there are a few more on top of these also, are recurrent neural nets, which is RNN, and we have convolutional neural nets, which is CNN. And some of you might defend CNN and RNN together forms ANN actually, like with the textbook approach, or like with the with how the theory has to be, right? But practically, I would say ANN is a separate component. Why? Because it's a separate classification. Because of the nature, we don't deal with the sequential data with ANN, right? It's used for image recognition, cool stuffs like that, but it's more of a feed forward network. When I say feed forward, right? So feed forward is like just one way from here to here, like from this direction to this direction, right? So such sort of simpler structures are feed forward networks. While we also have something called back propagation, where the output layer feeds back to the input layer through some derivations or derivatives, which is called a convolutional neural network. Okay, is also, like I would say, is a pooled network. Is mainly used for image processing, right? We discussed about one example, because when you have some time series input, let's say yesterday's data, today's data, day before yesterday's data, like you have date wise, timestamp wise slice of that data, you will definitely go for RNN blindly, I would say. I mean, some of you might challenge me, but or techniques, but this is going to be a standard one. Okay, and we'll look at it like one by one. So the first thing is the gradient. So folks would have already had an idea of this, like when you tried out the traditional data science and machine learning, is basically you will try to find the gradient descent or the gradient descent algorithm, wherein you will see how the data points change over time. I would say rather it's not the actual value, it is the how the minimum like a lower value than the previous value, then it means that is also a local minima. The previous minimum is also a local minimum point. You will go on progressing until you reach the lowest value, and then after that you will see a steep rise in the value. I mean, this sort of going up and down and trying to find the lowest value is all about the gradient descent. And why we need this is, see, basically you need to understand the learning rate. Okay, how quickly you are learning the pattern in the data. It is both applicable in traditional data science as well as in deep learning. It's all same concept. Nothing has changed. The concept is same here also, right? Next is the activation function. Okay, what is activation function and why we need it? Why we need one? Okay, so we saw we have input. We also have multi layers between input and output. So the in between layers are called hidden layers, which is where the magic happens of the magic of deep learning happens basically. So when you don't have when things are linear, right? Like when I would wish to give you a different perspective of this definition basically. Okay. Because you might have a different definition. Obviously that is also correct, this is also correct, I would say. When you have the derivation or the derivative of the value that is normal, later why sigmoid has some complications with the complex networks, or it has some drawbacks with complex networking. Okay, you have tan-h, which is also one of the popular activation function, which is again for adding non-linearity to your layers. And you have ReLU, which is which is like a rectified linear unit, like, which is very commonly used in memory implementation, which is like to memorize what happened like in the past or the previous layer, so that your next layer could be optimized. We'll look at ReLU in some time. Okay, so you have these kind of activation functions, and I also tell you like why it is needed. It is needed to add non-linearity. Why non-linearity added is because in a layered approach, if you are trying to refine something through different layers, the derivatives should not get lost with the linearity, and that will completely collapse the neural network. I would suggest you to research more on why we need activation function, what is non-linearity, what non-linearity helps in the neural network space, right? Next is bias handling, and you want your system to automatically detect some anomalies in a live that is required because we need to tune our parameters. When I say parameters, is a parameter vector. Okay, everything is a vector again. So friends, like when I say like vector, because it's all directional. The input, the hidden layer, and the processing output layer is everything you see here is having a direction, and even the back propagation is will also have a direction, like from output to the input. That is also will have a direction. So it's all vector here. So we want to tune parameter vectors, based on the errors that happen at each layer. So that's why we need bias handling. Okay, we'll see like one example of we'll go through a code of RNN with Keras and TensorFlow. We'll see like where these things are implemented basically. Okay. Next up is a softmax layer. Of course, these two layers, these two techniques come before this softmax. Is one of the important step here, back propagation, because that is where you will start to learn. That is where the system starts to learn from the feedback. The feedback of the output is again driven through the to put in short. Let me just share my entire screen and then tell you from the perspective of notes rather than PPT. Okay, see I have the input layer with weights. Okay, and then I have hidden layer and okay. Yeah, that I'm trying to depict here. It's like it flows through your hidden layer. Okay, and then you have another hidden layer maybe. Okay, of n minus equals so. Okay, and then you finally have, like, it goes on. You can have multiple layers, and finally you have the output layer. Okay, so I can comfortably show you from an image from the internet, but I just want to basically tell you, like, emphasize here. So that's why I'm trying to draw things with just simple characters. Okay, here goes softmax. Okay, okay, so this is how this is the this forward direction is nothing but the feed forward network. Okay, and this is your back prop or back propagation. Okay, this is a process you will and of course, like, you will have activation function here. You will have like activation functions here. You will also apply some say customization functions here. Okay, so basically you will apply functions over here and here in the hidden layers and the output layer. Okay, but and then like we have, let me put it in functions. You receive the input, you have certain bias, you have certain of course, like it's with weights. So weights, when I say weights, we will have the W, the weight vector. I'll also explain you one of the recurring RNN architecture. Okay, you will further get an understanding with that. Okay, so the input is given, weight is multiplied. Okay, and then it's given to the hidden layer, where you will apply the activation function and try to make it non-linear, and then which is also like fed with a bias. Okay, and then that input is given to the next layer, so on and so forth, and finally you have the output layer. And in the output layer you calculate the loss, and that loss is again fed back to the input through the same hidden layers, like the in-between intermediate layers, to basically avoid the dropouts, or like to tackle dropouts. And dropouts is altogether a different technique. I've not listed here, but I want you folks to research more on that. Okay, I'll give all of these takeaways as part of the I will give all of these takeaways as part of the end of the session, so that you can go back and learn more about it, because it has its own significance. Okay, and last is cross entropy. I won't say it's the last. Actually, these two come before softmax. Softmax is going to be the last step. Okay. So cross entropy is like, if you all know the thermodynamics, it's the same concept. It's the same theory, wherein like how deviant is your prediction is, like it's basically labeling the data, or like trying to apply the label on your unlabeled data. And when you try to do that, how much deviant is your labeling is the cross entropy. And you again apply certain functions. You can reuse the activation functions, different types of activation functions here as well, but there's a different set of weighted functions available for this handling cross entropy. And all these when I say like right from bias handling till cross entropy, all of them, all of these techniques are basically dealt with loss function, improving the efficiency and accuracy, is all dealt with these concepts only. Okay, so folks, we've discussed about the various techniques. This is common across any deep learning neural network implementation. Please make a note of it. Okay. Next up is for our case of time series data, we will choose RNN, because that's what most suitable. But RNN has its own disadvantages. It has a very popular common problem called vanishing gradient or exploding gradient. Why? I would say with a small example, and I say right. This is like with some weight vector, like this is a neutral word, this is a positive word, this is a negative word, kind of that weights are given as and when like the input is getting processed. But what happens is, as this sentence goes through the various layers, right, the intermediate layers, the RNN suffers from what happened in the past. Like it could not have multiple layers. Okay, that's why it is h dot dot dot, like you will have multiple layers before you reach output. And u, of course, u vector is the weight vector for the input, and w is the weight vector for the hidden layer. Okay, the hidden layer is also like connected, as I said before. In RNN, your is recurrent neural network. So remember the word recurrent. So actually, the input of the other layer or the other hidden layers are actually connected. They are interconnected with various time spacing. Okay, so they're all connected layers in between. Okay, and the processing is impacted by the input from the other layers also. All right, always remember that. Finally, you have output of the hidden layer is fed to the final output layer with weight of v vector. Okay, and we basically depict this as y hat of t, y hat of t plus 1 and y hat of t minus 1. Of course, like this is, and this is the depiction of LSTM and GRU. Okay, why is, because certain memory for this this C component. Okay, it basically makes use of some memory, transient memory. Your GPUs have some memory like 2 GB, 4 GB, whatever the configuration it could be. So when we use the LSTM out of Keras API, it basically reserves certain memory by itself. Okay, and here you can see like the I is a input gate, and F is a forget gate, and O is the output gate. Okay, these are gates. Why? Because you can control these gates. Basically, gates are meant for controlling the inflow of outflow of data. Okay, if you see, when you have certain data, okay, let's say in our case, like example, we saw like this kind of a sentence, right? We could have a lot of other information in between this sentence, which could be irrelevant also. Okay, and we don't want that to carry forward all together, like all the way till the output. To forget, it takes the loss function output from the from the back propagation. It tries to forget certain things so that the result is accurate. Okay, the memory cell, of course, it has the memory cells store the value of certain loss function values and outcomes. Okay, so basically, like is C is new and C dash is the C is the memory cell, C dash is the new memory. So when I say new memory is see, these are all recurrent stuff. Okay, something you have in memory. Okay, this is about the LSTM implementation and internals of LSTM. And we have GRU, which is gated recurrent unit, which also has this basically H and H dash. Why? Because this is activation and candidate activation. And you also have something called a very special thing called reset gate. Forget gate and reset gate would be one of the same in some aspects, but reset gives you more control, like how you can reset a computer or reset a mobile phone or a gaming device, right? So reset gives you a more refined control of when you want to reset it and clear off. Okay, so GRU is more memory optimized, I would say, in that aspect, and that's why GRU is advanced version of LSTM, I would say. But still, it's some of the aspects are still evolving in that space. Okay, so just remember, solve the vanishing gradient or the memory loss problem of recurring neural networks. Okay, think in that perspective always. You'll have a good understanding later on, like when you start implementing. Okay, so with that we have come the RNN, which we talked about, and the time series forecasting with it. And way forward, we'll come to it. Way forward is, these are some of the pointers or the buzzwords that I want you folks to go and research on it, because they have a lot of scope, especially with the time series forecasting with the deep networks or the deep learning. Is the implementation of autoencoders. And next is the very important one is you can Google this and search probabilistic time series prediction. What it means is, when I give an input and that goes into the various layers, and I predict an output in the future, what will happen in the future, right? and that is not one single thing that could be a probabilistic. I can have a range of output that can happen in the future. I want you guys to go and research about it. And next step is there is a very cool library that came out. It's called the state of the art AI. It's a TS AI, and there's an implementation out there which makes use of the TS AI for time series forecasting with the deep neural networks. Okay, so that's why I'm not able to showcase with my anaconda, but I can go over the actual code that can be used. Okay, so if you can see, I'm trying to import all of these, you guys would have already know. I'm just importing all of these pandas and plotting libraries. Okay, the special one is here is the keras. Okay, you need to import keras, which is as given as part of the TensorFlow library, which is specifically for deep learning, and we'll make use of using that. And from scikit-learn, I'm using the scalar, and then the mean skew. Of course, this is for calculating the errors and testing, the improvising the accuracy. Scalar is you want to scale up your vectors that you feed as an input for the intermediate layers. And of course, this is NumPy. Okay, so an IoT data, okay, which is pretty much timestamp and then a value of the sensor output. The sensor could be anything. Let's assume it's a pressure sensor. Okay, so timestamp wise, what was the output of the sensor? Okay, so just 2 columns, and we will use the output column here. Okay, while we read as the CSV dataset, and we plot and see how it is being distributed. And someone asked what is seasonality. So here you can see can you see this pattern here, this pattern and this pattern, and here again, here there is an upward trend and then a downward trend, a trough. Okay, so this is about seasonality. So this is seasonality, it could recur back in time again, the same pattern. So you in traditional world you will handle with moving averages. Okay, so let me in the interest of time, let me quickly go over. This is I'm doing it to normalize my data set. Okay, and I split the test and train data set 70-30, 80-20, up to you. You choose whatever your test and training data set. Okay, and then it's the same stuff I'm doing again, and you can see what is the length of the test and training data set. This is the actual data set, the scaled data set or normalized data set. Okay, and then what I try to do here is you would see something similar in a different deep learning network implementation also. Okay, what we try to do is we got it from the CSV, we have normalized it all up to here. It's all fine. It's the same even in your machine learning and data science also. Here we want to feed this into our keras and LSTM. Okay, and that's why we are defining a function here. Okay, so I don't want to go in depth into the function, but you will do something similar in every deep learning implementation, just to make fit fit your transformed or not transformed, normalized data set into your keras library or keras data set. Okay, because your deep learning library has to understand how the data has been shaped. Okay, and in the process of that, we will define something called, see, this is look back and all this is are variables, but what it is basically and what weight you have to give. We have the weight vectors, right? We saw all the way, right? So it's all about feeding all those values, right? And next, we just check on the shape of the train X and train Y, basically, and the test X and text Y. So basically the we want to we want to break down and split our matrix, the combined data of the time series and then the output values as input and output separate vectors. Okay, that's what I'm trying to do here with this test and train split, and then I create a data set so that I have separate data sets for each of them. Okay. Finally, the reshape is, I mean, this reshape again, this you would see such reshapes in any other implementation also. Why is because again I told you, right? So basically you give the sample, you give the time steps, give the feature, like so the input of the hidden layer has to give to the becomes the output of sorry, the output of the hidden layer becomes the input for the next hidden layer, right? So that's why you have such a reshaping to be done. Okay, so basically I have chosen, like, just immediate value over here. Okay, and 0 and 1, like this is just the immediate values I've given. When I say I, it's like, in this example, it's not like, I wrote this code. So finally feed it to an LSTM. Okay, we saw this LSTM, right? Which has the memory, the forget gate, which has the memory cell and the output gates, etc. Right? So it's just implementation of here we choose the sequential model because we are going to use RNN. Okay, and that's why we invoke sequential, and then we just add an LSTM to it. It's just one single line, that's it. And then you add how many layers you want. Here I've chosen like one layer. The dense of whatever that you number you give, you will have that many layers. Okay, hidden layers. And then you will invoke the compile with the loss to be the mean squared error. And this mean squared error, we saw, like, we are making use of the scikit-learn's library. We would have somewhere we would have defined. You see here, we give this mean squared error back here, like, basically tell the compiler, like, this is what the loss function is going to be. And the optimizers, I'm not going to go in depth into it. There are like bunch of optimizers available. Equal to 2 is basically like, the layers that you have, the number of layers, and batch size is like how much of the input size that you want to give, and epoch is how much of the time frame that you want to have. Like, you will choose 100 it will choose 100 timestamp data points for one single for one single run of a input, for a one single input vector, basically. Like, it has to go all the way. So what does is, like, Keras start to calculate losses. We talked about back propagation, right? So these losses will be used in that back propagation. Okay, next up is we need to do the prediction, right? So the prediction is nothing but just like with the libraries, just dot predict, that's it. Dot model, you get a model. Dot predict, you get the prediction. So that prediction data sets you have, again you want to annotate. Someone wants to annotate. Basically you take the predictions, okay, you invert them. Why you need to invert them? Check this, because it's one of the steps that you will do commonly in every deep learning exercise. And then you finally calculate the root mean square error, like, which is RMSE, to basically to reduce the loss. Okay, so it's more towards like finding out the accuracy. Okay, so you get the score. This is like how traditionally you have the machine learning and data science, same scikit-learn, same RMSE, okay, library that you are making use of here. Finally, I try to multivariate analysis and multivariate vectors, right? You want to shift them so that is basically part of the back propagation process, right? So that's why you have this look back variable being utilized here, and then you reassign the same to your train predict and train test predict. Basically you feed it back to the input layer. That's what you are trying to do here, basically. And the shifting of multivariate features is a very common thing done in any deep learning exercise. You might want to check on that as well. So finally, if I plot, you can see, this is my input, and blue is my predicted value. Okay, and this is the test value. Okay, so which is the actual result. As you can see, like the deviation is very much either way, like the blue line is a predicted output. And do the time series forecasting for a deep learning. You did not do any sort of auto regression. You did not do any sort of moving averages. No fancy manual stuffs that you had to do intermediates here. Is pretty much a very short implementation. Given if you had to implement with a traditional data science approach, you would have a lot of errors. Plus, you would have a lot of manual. It can be implemented on any data set, like it's a kind of a simple time series data set you can have. All right. So check on these things. Okay. These stuffs. I'll paste it on chat and wait for